Well, it's 8 o'clock. Everybody looks like you're all bright-eyed and bushy-tailed after a whole week of rest and relaxation. Just to do a kind of a quick review of where we were before we broke a week ago. On chapter 6, we started looking at work and energy. And we found that work is force times distance. And we looked at the difference between, thank you, work that is done, did you sign in yet? Work that is done by conservative forces and work that's done by non-conservative forces, and the work that you do on an object as opposed to the network that is done on an object. And we saw that when conservative forces are at work, when non-conservative forces work, the energy of a system changes. You can add energy to a system. That's you. If you're pushing on the box, you're adding energy. The work can be dissipated, energy removed from the system in the form of heat. These are non-conservative forces. And they're called non-conservative because when they are at work, the energy of the system is not constant. It doesn't stay the same. It changes, either by having energy added in or by having energy taken out. Then we looked at conservative forces. We looked at two examples. We looked at the gravitational potential energy, and we looked at spring potential energy. And we saw how these conservative forces can do work without energy being, they can act without changing the amount of energy in the system. That as long as it's only conservative forces at work, the total energy of the system will remain unchanged. And we're talking about mechanical energy here. So we have the total kinetic energy plus the total change in potential energy must equal 0 if only conservative forces are at work. In the general case, this will not be equal to 0. It will be equal to the work done by non-conservative forces. Or actually, I guess that's minus the work done by non-conservative forces. What we did with all of this is we used all of this new information to build up to what's called the work energy principle. And this is going to give us a new and powerful way to analyze things, systems of objects and motion and forces, without having to go through and identify every vector force. And it will produce it. Okay, there will be times when you got no choice but to actually analyze the forces involved, especially when you're dealing with non-conservative forces. But this work energy principle gives us a very powerful new tool for analyzing some systems. Especially when there are no non-conservative forces at work, we can talk about the change in the kinetic energy plus the change in the potential energy will always equal 0. That means we will always know that the change in the kinetic energy will be equal to the negative of the change in the potential energy. And this is what is going to be the focus of our lab this week on Thursday. We're going to measure the potential energy of a dynamics cart on a track that's elevated and use that potential energy to calculate how fast it will be going when it gets down to the level track on the floor. By knowing how high above the reference level, the lower level track, by knowing how high above that track we start with this cart at rest, as soon as we let go of it, that potential energy is going to be converted into kinetic energy, which we can solve for a velocity. And you'll be sitting there with the stopwatches and timing how long it takes the cart to travel a meter along the long, flat, level track, and that'll give you that velocity, and you'll be able to compare it to the potential energy that it started with. We're also going to use, we're going to do a second version of it where instead of gravitational potential energy, we'll be using spring potential energy. In which case, we'll look at the change in kinetic energy will be equal to the negative change in kx squared or just kx? It's kx squared. Thank you. If you know the spring constant, K, of a given spring, and you know how far you compress it, then you know how much potential energy is stored in that spring. And once it's released, you can calculate how much kinetic energy, how much velocity it's going to produce. Now, they worked through an example here of falling rock. So before we go into this example, let me stop and back up just a little bit. Does anybody have any questions about the homework assignment? Remember, week 11's assignment is due right now in class today. So does anyone not have week 11's assignment finished? Okay. Has anyone had any questions about the homework assignment? Any of the problems? Any of that stuff we need to go back and look at and help you sort out how to solve it, how to work it? Okay. Who thinks the person sitting next to them has questions about something that they ran into in the homework assignment? What do you think he doesn't know yet, or he wants help with? Okay. No, I want to help. I really do want y'all to get this, so, you know. Go ahead. Number 16. Page 164. If the kinetic energy of a particle is tripled, by what factor has its speed increased? And that's A. Okay. So we got A. 3 times the kinetic energy. That equals 3 times 1/2 mv squared. So they're asking by what factor has the velocity increased. So we solve for velocity, and that is well, first of all, velocity would be, here we got 3 times x is equal to 3 times 1/2 mv squared. So 6x equals mv squared. 6x over m equals v squared. And so the new value of v would be the square root of 6x over m. This would be compared to just x equals 1/2 mv squared, which would be 2x equals mv squared, and 2x over m equals v squared, and so v would be the square root of 2x over m. So v has increased by the square root of 3. We factor out the square root of 2x over m. We get the square root of 3 times the square root of 2x over m. So in order for the kinetic energy to triple, velocity would increase by the square root of 3.
That's what I wrote down that I was just guessing.
Okay. Well, now on B, if the speed of a particle is halved, by what factor does its kinetic energy change? Well, 1/2 m v over 2 squared gives us 1/2 m v squared over 2 squared. So its velocity changes by 1 over 2 squared, or 4, 1/4. Its velocity would be cut in fourth, be reduced by 4, or to 1/4 of its original value. Does this make sense to everybody? Anybody have? Okay. Okay. Good. That's what it takes to get there. I would hope that your guessing was at least guided by some level of intuition you may have garnered from having studied the material.
Well, yeah, but I was looking at the formula and I saw the 3 and I was just
Yeah.
that sounds about right.
Yeah, all you do is you look at the formula and you know that kinetic energy is proportional to v squared. So if kinetic energy triples, then v squared will increase by the square root of 3. Or v will increase by the square root of 3. Or the other way around. Are there any more questions from the homework? All right, well then let's go back and let's look at this example. They talk about a falling rock. I'm on page 151, example 6-7. Now you understand, if you'll recall, we looked at this earlier when we talked about potential energy, that you can define any level as zero because all that matters is relative change in height, relative to whatever level you arbitrarily choose as zero. So if we say this tabletop is zero, then if we're dropping something from here, then we measure the distance from the tabletop to there. All right? Now in this case, we're starting with the dropping a rock from a height of 3.0 meters. And they say, calculate the rock's velocity when it has fallen to 1 meter above the ground. Do you notice that at no time do they tell us the mass of the rock? Why might that be? Look up here at the equation that we're going to be solving. Because we're talking about gravitational potential energy, mass cancels out. The only way that the size of the object would come into play is if its size is great enough that it's going to reach terminal velocity before it gets to the ground. Okay? But we're not going to deal with anything close to that range. Does everyone understand what terminal velocity is?
Isn't it where it reaches like the peak speed?
Yeah, but that is exactly, it's the fastest an object can fall through the atmosphere. The question is why? What causes it? Go back to our force vectors. When you have an object falling through the atmosphere, it's being accelerated by gravity. That's the vector force that is causing it to accelerate. But is that the only vector force acting against it? Air resistance is pushing up, opposing its motion. And it is that force of drag, of air resistance, is proportional to its velocity. Now that means that at some point, this object is going to reach a velocity where the drag is equal to minus the force of gravity accelerating it. And when those two vector forces are equal and opposite, they cancel out to zero. When the net force acting is zero, acceleration, mass, force, the sum of the forces equals mass times acceleration. Well, when the sum of the forces becomes zero, acceleration is zero, and the velocity remains constant. So if you ever take up skydiving, and as you're falling through the air, if you're spread eagle, laying out flat with your arms out wide, you're going to fall no faster than 120, 130, maybe 140 miles an hour, depending on how fat you are. Okay? I'm going to be a lot closer to 120. Y'all are going to be a lot closer to 140. But if you go into what's called a bomb out position, where you tuck your arms in and you point your head down, so you're only presenting this cross section. Okay, my cross section may be a little bit bigger than the rest of y'all's, but not much. At that point, we're all going to get pretty close to 170, 175 miles an hour, something like that. Okay, this is the mechanism. It's called terminal velocity. Has absolutely nothing to do with our subject matter this week. But since we're talking about objects falling through the atmosphere, I want to make sure you understand we're only going to be dealing with things moving at speeds slow enough that that force of air resistance is going to be negligible. Now, we're talking about calculating the speed of a rock. It's been dropped from a height of 3 meters. All right, y'all, you know what this means. We're about to do arithmetic. Get out your calculators. Height is 3 meters. So, now when we're holding it, up 3 meters off the ground, its motion, it is not moving. So V1 is 0. That means its total energy is its mass times 9.8 times its height, 3.0 meters. That's the total energy it has. Now we need to know what is its total energy at once it's fallen to a height of 1 meter. Well, now it's going to be equal to ½ mv 1 meter squared plus m times 9.8 times 1 meter. And that's equal to the total energy, which is still m times 9.8 times 3.0 meters. All right, now you can see right there, we can immediately divide through by mass. So mass no longer matters. Now we've got 1/2 the velocity at 1 meter squared plus 9.8 times 1 is 9.8 is equal to 3 times 9.8. So, so 1/2 its velocity at 1 meter squared will be equal to 2 times 9.8 meters per second squared. We want to solve for velocity. Now it's equal to 2 times 9.8 times 2, which is, what's 4 times 9.8, somebody? Equals 39.2 meters times meters per second squared. And so the velocity at 1 meter is equal to the square root of 39.2 meters per second. What's the square root of 39.2? 6 point something. Is that what the book got? 2.6? Okay, so it's 6.3. See how we figured out how fast its instantaneous velocity at that moment when it's 1 meter off the ground would be? And we never once had to do vector sums of forces or anything else involved, because only conservative forces are involved. If we wanted to solve this to find out how fast it would be going when it hit the ground, change that to a 0. Does anyone have any questions about what we just did, how we solved that? All right. Look at another example out of the book. They like this roller coaster example. And they draw this roller coaster at that's how they've drawn it. Now they're saying in this example, the example I'm looking at, by the way, is page 152, example 6.8. Now they're saying we're going to set y equal to 40 meters. Well, that's an awfully tall roller coaster. They said 40 meters. You realize 40 meters is like 120 feet. It's like a 12-story building, but okay. I guess they make them taller than when I was a kid. Not that I rode many of them when I was a kid. Now what they want us to find out is, assuming it starts from essentially rest right here. Wait, is that what they said? Because we don't have to. No, they say starts from rest at the top. Let's work it the way they did, but then I want to go back and look at it, because this is part of the power of this whole work energy principle. We don't have to assume that it's at rest at the top. We can assign it some value of some velocity, some speed that it's moving at the top of that hill, and that's just the kinetic energy part of its total energy at that moment. Okay? And as long as we're dealing with strictly conservative forces, which is a way of saying as long as we ignore the friction between the car and the track, and between the drag between the air and the cart, then it doesn't matter what its initial velocity is. Book says 0, so since we want to get the same answer they get in the book, we'll say it starts at rest. They want to know how fast is it going when it gets to the bottom of this hill. But then they want to know at what height will it be when its speed is half. Yeah, will be half of its maximum speed here at 0. So let's start. What's our total energy to begin with? It's 1/2 mv squared plus mgh. Which equals 0 plus m. What's 9.8 times 40? 392. Which is meters per second squared times meters. So it's meters squared per second squared. And that is our total potential energy. But it's our total energy completely, because we have no kinetic energy that's sitting at rest. So whenever y is 0, this same number is going to be equal to 1/2 m times v at 0 squared plus m times 9.8 times 0. Okay? Well, it's pretty easy to solve this. We've got, in one case, we've got mass times 392 meters squared per second squared is equal to 1/2 m times velocity squared. M's cancel out. What's 2 times 392? Say again? 784 meters squared per second squared is equal to velocity squared. And if you take the square root of both sides, 28 even. So at the bottom of this 40-meter drop, its total velocity, its velocity is now 28 meters per second. What is half of 28 meters per second? 14 meters per second? Okay, how high will it be going up to here? What height will it be at when its speed is down to half that? Or when 1/2 m times 14 meters per second squared is equal to mass times 9.8 times h. So what is h? M's cancel. 14 over 2 is 7. Oh, that's not 14, though. That's 14 squared. What's 14 squared? 196. So we've got 196 meters squared per second squared divided by 2 times 9.8, because we're dividing out by g, is equal to h. So what's divide 196 by 2 and then by 9.8? Say again?
960.4.
No. No, you can't divide 196 by 2 times 9.8 and still come up with more than.
Yeah, that's what I was getting confused. I was like,
You got 10 even?
Yeah.
Okay, so H and N would be equal to 10 meters. And that's why you don't trust me to do arithmetic in my head. Is that what the book says? Why are they subtracting? Did I swap out a sign somewhere? Yeah, they're coming up with 30 meters. They're subtracting that 10 meters from the 40. And I'm not sure. Okay, this is it has 28 meters per second at the bottom. At what height will that 28 meters per second be 14? This is oh. Okay. I got to going too fast apparently. So let me make sure I understand what my mistake is here. I see what they're saying. They're saying what potential energy would be half of that total kinetic energy. And no, that's if you have that 190, if you have that 14 meters per second, this is zero potential energy, all kinetic energy. So it's 28 meters per second here. At some height, its kinetic energy will only be half of that, which means its potential energy would have to be the other half. Here at y equals 0, the kinetic energy plus potential energy is equal to 1/2 mv squared plus mg times 0. So its total energy is this kinetic energy. At this point, its kinetic energy, its total energy is going to be its remaining kinetic energy plus that potential energy. Change in kinetic energy is equal to minus the change in potential energy, which means okay, this total energy would still have to be equal to, okay, no, you know what? They are right. I got ahead of myself, going too fast. And I want y'all to, everybody pay attention, because I want y'all to see where I went wrong. The total energy here is the kinetic energy at the bottom at 0, at y equals 0, plus the potential energy at y equals 0 is still equal to mass times gravity at 40 meters. That is still the total amount of energy in the system at all times. Okay? That means when it gets to h, when it gets back up to h, its kinetic energy at height h, the unknown height, plus mass times gravity at that unknown height must still be equal to mass times gravity at 40 meters. Does everyone see this? You see where I got ahead of myself? Say again? Right, this is what I'm saying here. I've got this kinetic energy at height h, plus the potential energy at height h is still equal to mass times gravity, times 40, times the total potential energy that we started with. Okay? If I wanted to say it differently, I would have to say the kinetic energy, and this is basically what I was almost doing, but not quite, was I said the kinetic energy plus mgh would be equal to 0, in which case mgh would be equal to 10. But the kinetic energy at the bottom is not equal to 0. The kinetic energy at the bottom is equal to 28 meters per second squared. That total kinetic energy, which is the same as this total potential energy. That's where I made my mistake. It was right here when I said this kinetic energy, when does this turns into, anyway, at this point what you do is you solve by finding the kinetic energy at h is equal to mass times gravity at 40 meters minus mass times gravity at h. And that's equal to 1 half m the velocity at h squared. Now we can cancel out the masses, and we've got 1 half velocity at h squared is equal to 9.8 times 40 minus 9.8 times h. Now, when we solved for h was 10, but what we're actually looking for is 40 minus h, which is 30. Does everyone understand what just happened here? We know how much the kinetic energy is going to change through that h, through 10 meters. Somebody give me some indication. Does everyone understand what's going on, how we did this? Say again? Yeah. All right. Well, let's not take any risks. Let's repeat this process just to make sure we've got it right. We have a mass m at 40 meters times gravity that has 0 velocity. And that gives it a total energy of mg times 40. That is was mgh. Equals mg40. At the bottom, the height is 0. So that mg40 is now equal to 1 half mv squared plus this goes to 0. So the total potential energy has been converted into the maximum velocity. That was our 28 meters per second at the bottom. Now the question is, at what height h will v equal 14 meters per second? So at height h, the kinetic energy at h plus the potential energy at h will still be equal to 1 half m times 28 meters per second squared. Okay, it's still equal to that same total energy. So at h, we know that the velocity is going to be 1 half m times 14 meters per second squared plus m times g times h. And all of that will have to be equal to 1 half m times 28 meters per second squared. Everybody with me so far? The total energy has to stay the same at every point. Now we can simply subtract this . 28 meters per second squared minus 14 meters per second squared. What does that give us? What's 28 squared minus 14 squared? Somebody? Say again? 588. And divide that by 2. 294. And if we divide 294 by 9.8, equals exactly 30. So, as long as you're careful not to get ahead of yourself, do you see how this can greatly simplify working out problems like this? Now, let's do one that is not in the book. Wait. Yeah, we've only got a couple more minutes. I would point out to you that we started off with an initial kinetic energy of 0. But what if it had started off with a kinetic energy of, it was moving at 2 meters per second as it rolled across the top of that hill? Because if you've ever ridden a roller coaster, you know that that chain drive drags you up the first big steep hill. And when you get to the top, you're not at rest. You're actually moving along at some slow snail's pace, but you have some kinetic energy. That wouldn't really change any of the math that we did. It would just mean that your initial kinetic energy is not 0, but your total energy of the system does have to stay the same. Right? Any questions? All right. See y'all tomorrow, I'll see y'all Wednesday.